And welcome to our video lecture on empirical formula, molecular formula, and percent composition. Our objectives for today, we're going to review converting between mass and moles. We're going to define empirical formula, a molecular formula. We're going to find empirical formula. We're going to define and calculate some percent composition. We're going to do some more empirical formula calculations, this time with percent composition or mass, and then we're going to wrap up with a look at finding the molecular formula of a compound if we're given the empirical formula and the molar mass. There are so many calculations today, my friends. So if you don't already have your calculator and a periodic table nearby, pause the video, grab them. You're going to need them. First up, let's do a quick review of some molar mass conversions. So if this is our given is 12.8 grams of carbon. We want to convert that into moles. Moles is our wanted. Go ahead and do that conversion here in the Nearpod. Hopefully you got 12.8 grams of carbon in the head of your railroad tracks. Because we have grams on top, we want it to go away, we're going to put grams on the bottom. We want to convert our grams into moles, so we're going to put moles on top. Remember that mass and moles, we're going to use our periodic table. How many grams in 1 mole of carbon? Periodic table says 12.011 grams in 1 mole of carbon. Our grams top and bottom cancel out. We're left with moles, which is good because that's what we want to find. With our calculators, 12.8 times 1 divided by 12.011 gives us a grand total of 1.065689. So many digits. How many sig figs shall we keep? How about 1, 2, 3? 1, 2, 3 sig figs. 1, 2, 3. That 5 is going to roll that 6 up to a 7. Our final answer is going to be 1.07. Unit label is moles of carbon. 1.07 moles of carbon is our final answer. So now I want you to take a look at this data table. We've got some structural molecules. I have a molecular formula and an empirical formula. I want you to think about the relationship between the molecular formula and the molecule. The relationship between the empirical formula and the molecular formula. Noodle on some potential descriptions or definitions for molecular formula and empirical formula. If you want to pause the video to think about this, you can. And here are some definitions. So molecular formula is the formula that gives us the number of atoms of each of the elements present in one molecule of the compound. This is all of the atoms of all of the elements. The empirical formula is a little bit different. This one's going to give us the lowest whole number ratio. So if I'm looking at, I'm going to skip to this guy. This is ethane. This molecule is ethane. There are 2 carbon atoms and 6 hydrogen atoms. Notice 1, 2 carbons, and then 1, 2, 3, 4, 5, 6 hydrogens. So our molecular formula is telling us the total number of all the atoms of all the elements in that molecule. The empirical formula, this is the reduced version, lowest whole number ratios. We're kind of taking 2 and 6 as a fraction and reducing it down to 1 and 3, our invisible 1 and our 3. This guy, C4H6, we can divide both of those by 2, and that's going to give us that reduced lowest whole number ratio of C2H3. This one, C3H8, this is propane. Notice that the molecular formula and the empirical formula are the same because there's really only one that I can divide both 3 and 8 by, which is going to leave the empirical formula to be the same as the molecular formula. That happens sometimes. Let's practice here. So let's say that I've got N2O4. I want to find the empirical formula. What is my greatest common factor between 2 and 4? Well, it's 2. So I can divide both of those subscripts by 2. The empirical formula, reduced lowest whole number ratios, is going to be N1O2. We can also write that just NO2. We can leave that invisible 1 actually invisible. So this would be our empirical formula. Sulfur hexafluoride. Let's write that formula so that we can find the empirical formula. So sulfur, I don't have a prefix here, so I know that there's just one S. Hexa is 6, so I've got fluorine 6. Invisible 1 here means I can only divide both of these guys by 1, and so the empirical formula is going to be the same as the molecular formula, SF6, sulfur hexafluoride. This guy, now I've got a picture, not a formula. Each of these dark gray balls is representing a carbon atom, and each of our lighter colored balls representing a hydrogen atom. So let's go ahead and count our carbons. There's 1, 2, 3, 4, 5, 6, 7, 8. Got 8 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 hydrogens. So my greatest common factor of 8 and 18 is going to be 2. So I can divide both of those by 2. And our empirical formula, this is our molecular formula, our empirical formula will be C4H9 when I divide both of those guys by 2. Empirical formula, molecular formula. All right, these ones are yours to do in the Nearpod. Make sure that you find the greatest common factor, divide all the subscripts by the greatest common factor, write this guy as a formula so that you can find the subscripts and then the greatest common factor. Remember that these dark gray balls are carbons. Count them all. The lighter colored balls are hydrogens. Make sure you count them all and find the empirical formula here in the Nearpod. Hopefully you divided all these guys by 6. Divide them all by 6, and then our empirical formula is going to be 6 divided by 6 is 1. 12 divided by 6 is 2. 6 divided by 6 is once again 1. Our empirical formula, CH2O, or you can leave the 1s in there if you want to, it doesn't matter. Molecular formula, empirical formula. Tetraphosphorus decoxide, remember that tetra is 4, so I've got P4. Oxide is oxygen, deca is 10, O10. I can divide each of these by 2, and so our empirical formula is going to be P2O5, empirical formula. One more. Carbons, I've got 1, 2, 3, 4, C4, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens, 4 carbons. This is butane. I can divide both of them by 2, and my empirical formula will be C2H5. Molecular formula, empirical formula. So now we're going to do this super cool thing called percent composition. Remember from middle school math that percent means part over whole times 100. Turn that into a percent. So we're looking for parts, we're looking for wholes, and then we're going to multiply by 100 to make it that percent. So if I want to find percent composition of oxygen and hydrogen and water, I'm going to do part over whole. And I'm going to start with oxygen part divided by the whole, which is water, times 100 to make it a percent. And then I'm going to do the same thing for hydrogen. Hydrogen's the part divided by water is the whole compound times 100 to make that a percent. I need to do this with masses. So I'm going to figure out in water, which is H2O, what is the mass of the oxygen in water? There's only one oxygen, so the mass of oxygen, the part of the compound's mass that comes from oxygen, is 15.999 grams. I'm going to divide that by the mass of the whole compound, the water. So we've got 2 H's, each is a 1.008. I'm going to add to that one oxygen, 15.999. Our grand total is 18.015 grams per mole is the molar mass of water. So oxygen was just that 15.999. The whole water's mass is 18.015. Multiplied by 100 to make it a percent. When we do that math in our calculators, 15.999 divided by 18.015 is going to give us 0.88809, lots of digits, times 100. We're going to get 88.80. I'm going to leave it right there. 88.8% of water's mass comes from oxygen. I'm going to do the same thing now for the hydrogen. So let's find hydrogen's mass. Hydrogen is 1.008. But in water, there are actually 2 of them. So I'm going to multiply that by 2 because I want all the hydrogens that are in the water. So I'm going to do 2 times 1.008. I'm going to divide it by the total mass of the whole compound, water, which we found up here was 18.015 grams per mole, times 100 to make it a percent. So I'm going to do 1.008 times 2 on my calculator. That's 2.016 divided by 18.015 gives us a grand total of 0.1119086. Lots of digits. Times 100 is going to give us 11 point, I'm going to round to it to 11.2% hydrogen. So what this means is that 88.8% of the mass of water comes from oxygen and 11.2% of the mass of water comes from hydrogen. Percent is simply part over whole, and we're going to find the part of the mass of one element divided by the whole mass of the whole compound. Then we'll do it again for any other elements that are in the compound. Good? So to summarize the steps that we follow to find percent composition, we're going to find the mass of each element using the periodic table. With H2O, we figured out that hydrogen was 2 times 1.008, and oxygen was that 15.999. We found the mass of the whole compound. When we added those together, we got 18.015 for the total mass of the whole water. We divided the mass of each element, the 2 times 1.008, 2 times 1.008 divided by 18.015. We did the same thing for oxygen, 15.999 divided by 18.015. Divide the mass of each element by the mass of the whole compound, and then multiply by 100 to convert to a percent. Good? Do this one on your own in the Ed puzzle. Find the percent composition of carbon and of hydrogen in methane, CH4. So you want to find the part that's just carbon out of methane, and you also want to find the part that's just hydrogen out of methane. All right, go. So carbon in methane. So the carbon out of the CH4, carbon by itself is 12.011. The methane, we're going to have 12.011 plus 4 times 1.008. We add these together, 4 times 1.008 plus 12.011 equals 16.043. 16.043 is the total mass of methane. The mass of just the carbon is 12.011. Times 100 to turn it into a percent, and we get 12.011 divided by 16.043, grand total of 0.74867, lots of digits, times 100, 74.9% carbon. Let's do the same thing for hydrogen now. We've got 4 hydrogens in methane, so we're going to do 4 times 1.008, and then divide that by the total mass of the methane, which is going to be, again, that 16.043, 12.011 from the carbon, 4 times 1.008 from the hydrogen. So 4 times 1.008 gives us 4.032 divided by that 16.043 times 100 to make it a percent, and calculator says 0.2513, lots of digits. I'm going to round that to a 25.1% hydrogen. So the mass of methane, CH4, is 74.9% carbon and 25.1% hydrogen. Now we're going to take that percent composition that we just learned how to do. We're going to use it backwards to find the empirical formula. Remember that the empirical formula is that lowest whole number ratio of elements, atoms are the elements in a compound. So we can actually figure that out from our percent composition. So this problem is kind of the same as the last problem that you just did in the Ed puzzle. We're just going to do it backwards. So percent composition of a hydrocarbon, remember that just means we've got a molecule that is made up of hydrogen and carbon. 75% carbon and 25% hydrogen. What I'm going to do is pretend like I have 100 grams of the compound. If I have 100 grams of the compound, 75% is carbon, 75% of 100 is 75, which is why we choose 100 as our random number to choose. So if I have 75 grams of carbon, I'm going to convert that to moles. I do that by dividing by the molar mass of carbon. 12.011 grams per mole Calculator says 75 times 1 divided by 12.011 equals 6.244. Lots of digits. We'll stop there. Moles of carbon. Do the same thing for my hydrogen. So I've got 25% of 100 grams. 25% of 100 is 25. So we've got 25 grams of hydrogen. I'm going to convert that also into moles. We know that hydrogen is 1.008 grams per mole. Periodic table tells us so. Grams, top and bottom, cancel out. We're left with those moles. 25 times 1 divided by 1.008 gives us a grand total of 24.801. I'll stop there. Moles of hydrogen. So now what I'm going to do is write a formula. I could write C 6.244, H 24.801, because this is a possible ratio of carbon to hydrogen, but I don't love the decimals. So to get rid of the decimals, we're going to divide both of these numbers by the smaller of the two numbers. 6.244 is smaller than 24.801. I'm going to divide both of these numbers by 6.244. Doing that here gives me 1, which is nice because now I have a whole number, right? So this is the whole point. Scale this up to a whole number. So now I have 1 mole of carbon. When I do 24.801 divided by 6.244, 24.801 divided by 6.244, calculator tells me 3.97. I'm going to round that to 4 moles of hydrogen. So now, by dividing both of these by 6.244, I can write a better formula. That's C1, because this reduces to 1, H4, because this reduces to 4. And my empirical formula is going to be C1H4. Good. Steps that we followed. Convert percent to grams. You're just going to pretend like you've got 100 total grams of the compound, which means that whatever your percent number was becomes your gram number. Super easy. Then you're going to convert those grams to moles. You need to use the periodic table's molar masses to do that. Then you're going to divide all those mole numbers that you find from that step by the smallest of all those numbers that you can scale up to whole numbers. Sometimes you might have to do some rounding. Sometimes you might have to scale things up even more. We'll look at an example of that in a couple more slides. But first, think about these steps. Convert percent to grams. Convert your grams to moles. Divide the moles by the smaller of all the mole numbers. Go ahead and do this problem in Edpuzzle. Convert your percents to grams. Turn your grams into moles. And then divide by the smallest of those mole numbers to get a whole number ratio, and that will be your empirical formula. Do this one in Edpuzzle. All right, let's look at this answer. So 68.4% chromium, we decided to change our percents to grams. That's easy, 68.4 grams of chromium. We're going to convert our grams of chromium into moles of chromium. Chromium on the periodic table looks like it has a mass of 51.996 grams per mole, 51.996 grams per mole. Grams, top and bottom cancel out. And calculator says 68.4 divided by 51.996 is 1.315. Lots of digits. I'm going to leave it there. Moles of chromium. Let's do the same thing for oxygen. I've got 31.6 grams of oxygen because I'm just going to turn those percents into grams. Same thing, 15.999 grams per mole. And that's going to give us, calculator says, 31.6 divided by 15.999, 1.975 moles of oxygen. Good. So now I'm going to divide by the smaller of the two. 1.315 is the smaller of the two. 1.315, 1.315. And that's going to give us chromium 1. Oxygen 1.975 divided by 1.315 is, 1.5. So I have an empirical formula, CR1O1.5, which is not quite a whole number ratio because I've still got this fraction, or this decimal rather. So how do I get rid of a 0.5? What can I do to scale up to get rid of 0.5? We can multiply both sides by 2. And so that's going to give us CR2O 1.5 times 2 is 3. So our empirical formula, even though the math gave us CR1O 1.5, to get rid of that 0.5, we multiply by 2. 1 times 2 is 2. 1.5 times 2 is 3. Final answer, CR2O3. Here's another one that I want you to do on your own in the ed puzzle. But what's kind of interesting is that we don't have percents. We already have grams. That means you can skip step 1, percents to grams, because you've already got the grams. So you're just going to take those grams, turn them into moles, divide all the moles by the smallest, and then scale up if you have to. All right, so answers. 25.00 grams of sulfur, turn those grams into moles. Sulfur's molar mass is 32.066 grams per mole. So grams top and bottom cancel out. Calculator says 25.00 divided by 32.066 gives us a grand total of 0.7796 moles of sulfur. Do the same thing for oxygen. 25 grams of oxygen. Convert those grams into moles. We're going to put grams on the bottom and moles on the top. Periodic table says that the molar mass of oxygen is 15.999 grams per mole. So once again, grams, top and bottom cancel out. We're left with moles. 25.00 divided by 15.999. Calculator says 1.5625, lots of digits, moles of oxygen. Next step, we're going to divide both of these mole numbers by the smaller of the mole numbers, and that's this guy, 0.7796. So 0.7796, 0.7796. This one is math I can do in my head. It's equal to 1. So I've got sulfur 1. This one I'm going to use the calculator because it's a little bit messier. 1.5625 divided by 0.7796 gives us, it gives us 2. So oxygen 2. This is our empirical formula. If you want to write it with an invisible one that's actually invisible, you can do that. So either S1O2 or SO2. This is our empirical formula. All right, so let's do this one together. It's another one of those weird scaly ones. So we've got 43.6% phosphorus, 56.4% oxygen. Step 1, turn our percents into grams. Done. Good. Step 2, turn our grams into moles. 43.6 grams of phosphorus, turn those into moles. Grams on the bottom, moles on top. Periodic table says that the molar mass of phosphorus is 30.974 grams per mole. Grams top and bottom cancel out. We're left with moles. 43.6 divided by 30.974 gives us a grand total of 1.4076 moles of phosphorus. Let's do the same thing for oxygen. We've got 56.4 grams of oxygen. Turn those grams into moles. I've got grams on top. I want it to go away. Put grams on the bottom. Turn my grams into moles. Periodic table says that the molar mass of oxygen is 15.999 grams per mole. Grams, top and bottom, cancel out. Boom, boom. And we're left with 56.4 times 1 divided by 15.999. That's equal to 3.5252, lots of digits, moles of oxygen. Next step, we converted our grams into moles. Now we're going to divide the mole numbers by the smallest of the mole numbers. 1.4076 is smaller than 3.5252. So 1.4076 divided by 1.4076, I can do that math in my head. it's equal to 1. So I've got 1 phosphorus. How about this one? 3.5252 divided by 1.4076. Calculator says 2.5. Oxygen 2.5. You might be thinking, can I just round that up to 3? Not really. That's a lot of rounding. If it was 2.9, you could definitely round to 3. But 2.5, you're only halfway to 3. We need to do some scaling. With that 0.5, I'm going to multiply both of these guys by 2. 1 times 2 gives me 2. With the oxygen, 2.5 times 2 rounds this guy up to a whole number. Not rounds, scales. Scales this guy up to a whole number 5. So this is our empirical formula, P2O5. If you get a mole number that's a 0.5, you're going to multiply by 2. What if we had gotten like 1.3 repeating? What could we multiply to get rid of 1.3 repeating? You would multiply by 3. So multiply by 3, you'd get 3 and 4, and that would get rid of that 0.3 repeating. Same thing for 0.6 repeating. You could also multiply by 3. If you had like 0.25, let's say that you had 1 times 1.25, this you can multiply by 4. Multiply by 4, multiply by 4, and you'll get x4, y5. So this would be your empirical formula. If you've got a 0.5, multiply by 2. If you've got a 0.3 or 0.6 repeating, multiply by 3 to scale up to a whole number. If you've got a 0.25, that's the same thing as a quarter. Multiply by 4, and that'll scale up to a whole number. Good. All right. So now we're going to take that P2O5 that we found on the previous slide, that 43.6% phosphorus, 56.4% oxygen. We found P2O5. Now I'm given the molecular mass of the compound is 283.88 grams per mole, and I want to find the molecular formula. We found the empirical formula. We found the empirical formula by following our steps. Turn our percents into grams, turn our grams into moles, divide by the smallest, and then scale if we have to. We did that to find the empirical formula, but now we're being asked to find the molecular formula. It's another scale factor, my friends. So many scale factors today. So what we're going to do to find molecular formula, I'm going to find the formula of the empirical form. Oh, sorry, I'm going to find the mass. Find the mass of the empirical formula. The empirical mass, P2O5, is going to be 2 times phosphorus. Phosphorus was that 30.974. We're going to add to that our 5 oxygens, 5 times 15.999. 2 times 30.974 plus 5 times 15.999 gives us a grand total of 141.943 grams per mole of the empirical formula. Empirical formula's mass is 141.943. Now I'm going to take that molecular formula, which is the formula, the mass of the molecular formula. I'm going to take that guy, 283.88, divide it by the empirical formula's mass, 141.943, to find our scale factor. 283.88 divided by 141.943 equals 2. So that means that our scale factor is 2. I'm going to take that 2, I'm going to multiply all of my subscripts from the empirical formula by that scale factor of 2. And that's going to give us P, 2 times 2 is 4. 2 times 5 is O10. So our molecular formula is P4O10. Our empirical formula was P2O5. And I can go from the empirical formula to the molecular formula if I find the mass of the empirical formula, divide the molecular mass by the empirical mass, I get a scale factor. I multiply my scale factor by the subscripts of the empirical formula, and that's the molecular formula. Here are all those words in a list. So if you've got the empirical formula, you're going to find the mass of the empirical formula. Go to the periodic table, find the masses, add them up. Then you're going to take the molar mass, which is sometimes called the molecular mass. Molecular mass, molar mass, same thing. You're going to take that molecular mass, divide it by the empirical mass. I definitely forgot to write that in there. Divide the molecular mass by the empirical mass. Sorry about that. Find the mass of the empirical formula. Divide the big mass, the molecular mass, by the empirical formula's mass to find that scale factor. And then take that scale factor, multiply all the subscripts of the empirical formula by the scale factor. That's your molecular formula. Good. One more time. It's a lot of words. Let me fix this one first. Divide by the empirical mass. Good. Step 1, find the mass of the empirical formula. Take the empirical formula, add up all the atoms in the empirical formula using the periodic table. Step 2, find the molecular mass. It should be given to you in the question. You're going to divide that molecular mass by the empirical mass to find your scale factor. Use that scale factor, multiply the subscripts of the empirical formula by that scale factor that you just found to find the molecular formula. All right, so this one, 2-part question, and then we're calling it a day, my friends. I want you to find first the empirical formula. We have 5.9265% hydrogen, 94.0735% oxygen. First, find the empirical formula. Once you have the empirical formula, find the mass of the empirical formula. You also have the molecular mass here. Use that to find the molecular formula of the compound. Get ready, get set, go. All right, so to find the empirical formula, you're going to do 5.9265. Turn your percent into grams, grams of hydrogen. Turn your grams into moles. The molar mass of hydrogen is 1.008 grams per mole. So when we do 5.9265 divided by 1.008, we get a grand total of 5.879, lots of digits, moles of hydrogen. Do the same thing for our oxygen, 94.0735. Turn percent into grams, grams of oxygen, divide by the molar mass, 15.999 grams per mole. 94.0735 times 1 divided by 15.999 gives us 5.879, lots of digits, moles of oxygen. A little bit of deja vu here. Look, I've got the same number. I'm going to divide by the smallest. They're both the smallest because they're the same, 5.879, 5.879. So when I do that, my hydrogen turns into a 1, and my oxygen also turns into 1. My empirical formula is H1O1, or oh, good. So now that I have the empirical formula is here. Let's go ahead and find the molecular formula. How I do that? I need to find the mass of the empirical formula. HO is going to be 1 hydrogen, 1.008, plus 1 oxygen, 15.999, and that's going to give me a grand total of, calculator says 1.008 plus 15.999, 17.007, 17.007 grams. I'm going to take this, I'm going to divide the molecular mass by the empirical mass, 34.01468. divided by 17.007. Calculator says 34.01468 divided by 17.07. Oh my gosh, that's equal to 2. My scale factor is 2. So I'm going to take that empirical formula, H1O1, I'm going to multiply those subscripts, remember there's invisible ones here, by 2. And that's going to give us H2, 1 times 2, O2, 1 times 2. This is the molecular formula, H2O2. This is hydrogen peroxide. Empirical formula, molecular formula, molecular formula, hydrogen peroxide. My friends, we did it. You practiced converting between mass and moles. We defined empirical formula, molecular formula. Molecular is the actual number of all the atoms in the molecule. Empirical formula is the lowest whole number ratio of atoms of the elements. It's kind of like reducing our fractions. If you've got molecular formula, super easy to find empirical formula, just reduce that fraction thing. We calculated percent composition. Remember that percent is part over whole. So find the mass that's part of that's just an element, and then the whole compound, divide, multiply by 100 to turn it into a percent. We found empirical formula using percent composition and mass. Turn percent into grams, turn grams into moles, divide by the smallest scale if you have to. And then we found molecular formula if we have the empirical formula and the molecular mass. Find the mass of the empirical formula, divide the molecular mass by the empirical mass, and then use that scale factor to bump up your empirical formula to the molecular formula. You did it. Good work.